We're told that this demonstrates the Bernoulli principle and the way the Bernoulli principle produces lift on a wing. We're told that fast-moving air has lower pressure than still air. Unfortunately, this ignores the conditions which are assumed by the Bernoulli principle. The Bernoulli principle says that on a streamline, at two different cross-sections of the same streamline, because energy is conserved as the air moves along the streamline, the two forms of energy, pressure energy and kinetic energy, are summed to the same thing. And when one goes up, the other goes down in order to keep the same constant total value. That condition is not met here when we're comparing a jet of air over the top of the paper with static air underneath. These two pieces of air were never together on the same streamline. So the condition that's required by Bernoulli's equation doesn't exist. And let's try something else. Doesn't seem to work. Why not? Simply because the Bernoulli condition doesn't even exist in this situation. Why does it work here? It's because we're actually seeing a different phenomena. We're seeing Coanda effect. We have a jet of air going over the top of the sheet. It's entrained on the surface of the sheet. The paper is curved. When you have a jet of air traveling along a curve, it's being accelerated. The air is being pulled away from a straight line. And when air moves on an arc like that, it has a pressure gradient which keeps it in the curve. Higher pressure on the outside of the curve, lower pressure on the inside of the curve, and because the higher pressure gradient goes out to atmospheric pressure, the pressure on the surface has to be less than atmospheric, and the underside of the sheet has atmospheric pressure on it. So the sheet rises up. So this does not demonstrate the Bernoulli principle. It does not demonstrate how Bernoulli principle produces the lift on a wing.